Hello, welcome back to my channel, and in this video we're gonna keep discussing about the expectation value in quantum mechanics. So last time we find out what expectation value of actually mean, make measurement on one particle over and over again. That you can't do in quantum mechanics, so you have to make identical copies and try to measure all of them, and then you can find the expectation value. But last time we found out how to find the expectation value of x, but now we have in classical physics we find momentum, we find velocity, and we find kinetic energy. So how do we find the expectation value of those? So we know classically we know velocity is the derivative of position with respect to time. So let's just define this expected velocity as the derivative of this expectation value. We are talking about how fast the average position changes. It's not the speed of actual particle. You have to be careful about that. We don't have any way to figure out the real velocity of a single particle in quantum mechanics. In fact, in quantum mechanics, it's not even clear what velocity is. If particle doesn't have definite position, it doesn't have definite velocity either. So for now, we will just say the average velocity is same as the time derivative of the average position. Okay, so now we have defined this, we have definition of this average velocity. Now we can actually go and calculate this. So now we have this definition. Now we can calculate this, and we have done this calculation before in the wave function normalization, where we try to define normalization doesn't change with time. It's the same definition. We have this derivative. We know the definition of this average x. In last video we knew this definition, and we're just gonna take derivative of that with respect to time, and this derivative d over dt gonna go inside the integral, and we're gonna differentiate this size square. And we went through the whole process how we get this function, and you can watch in the normalization video. We're gonna try to go and simplify it further. Okay, so one thing I'm gonna do a mathematical what is it called integration by parts. So let's go over that and how we use this in this. We're gonna use integration of parts to simplify this, and so let's see how can we use this. Okay, so we know if I take the derivative of two functions, then we can apply chain rule, which is keep the first name, multiply take the derivative of the second, and take the derivative of the first, multiply with the second. Now I can apply the integration on both side from a to b, whatever the limit is, and this goes as you would know normal integration. And we know this side is just gonna become fg. So if I want to take everything, if I want to calculate this integral, I'm going to keep it on one side and take everything else on the other side. If you look at the first integral, it matches with our own definition, what we are trying to see it here, and it's going to simplify this expression, and you're going to see it in much more neater way. Let's apply this to this integral and see how it simplifies. So now we have this integral where we have this x time this derivative of some this phi, and all this combination of this phi and derivatives, and you have your this integration by part. Now in my integral, f is x and g is this whole expression. Now we're gonna substitute that in. And one of the thing we need to make sure we understand that whenever if your wave function is normalizable, whenever these x goes to infinity or minus infinity, your function should go to 0, as we have seen in last video. If your function is normalized, this is the condition that it must satisfy. Okay, so now I plug that in my expression here. Here is my f, here is my g, and this is my limit b to a, and this is dx over df. This is gonna be 1. And now, and if I when I apply this limit into my this expression, this is gonna go to 0 because of this limit. This should be a limit, not log. This is a typo, but this is gonna go to 0, this is gonna go to 1, and you're gonna left with this expression. Now we have simplified the expression from looking like this. Now we can further simplify it. So now we have our expression this. We can again multiply integration by part. On this section you see we have this derivative, and that is multiplied with a function, so we can apply integration by part, and with same limit. This is your homework, you're gonna do it, and you're gonna get a simplified answer where this 2 is gonna go away because it's gonna add up, and you're gonna get this simplified expression. And this is what you will know as average velocity. Quantum mechanics, we like to deal with momentum rather than velocity. Even in classical mechanics, average momentum here comes out this, because this m and cancelled out. You have minus h, this reduced Planck constant, and you have this integration, and we can generalize it, this average expectation values. So if I want the expectation value of x is conjugate of this psi, and then multiply with this your x, what is known as operator, and then multiply with your psi function, wave function, and take the derivative, take the integration. And similar, if I want to calculate the momentum, I have this expression where I change momentum to this expression, if you want to calculate the expectation of value of quantum mechanics. And this is very important when you are trying to calculate the expectation value. And this is we're gonna do more in next video. How do we calculate this is momentum, how do we then calculate the expectation value of kinetic energy of anything else? So this is how you calculate, and this is, you can consider this as an operator where a momentum operator is minus I h over dx, and for the operator of position it's just x. So I hope you like this video. If you do, give the thumbs up, and I will see you next time.